I record all the classes, and so if you miss a day, then you can go here and you can catch up with that day. So like for example, there's some help sessions that we had, and this is the screencast from April 16th of 2019. And then likewise, you're going to have a screencast from the 21st of January today. Okay? So if you missed today, you haven't missed today, obviously, right? Because you're here. But if you did miss, then you can go and catch up on the notes. I've already showed you the old exams. You'll have an equation sheet on every test. Don't be freaked out by this because there's really not a lot of math in this class. There are relationships I was talking about. There's not a lot of numbers. You'll have very few numbers on your exam. In fact, there's no calculators allowed on your exam or quizzes. You might have some very simple math like 10 divided by 5 kind of stuff. But mostly we look at relationships. And you'll see what I mean by that. How do variables relate to one another? If I change one variable, how does it affect another variable? Okay? That's the one drawback of your book. Sometimes, not very often, your book will give mathematical problems. And you sort of read through them. Don't get bogged down in them, but read through them and sort of think about what they do. But we're not going to have a lot of math. This isn't really, not a lot of math for this class at all. Does that make you feel better? Yeah, math is kind of important, right? Even for you guys, for you guys, no, it's very important. Okay. All right. Equation sheet. You'll have that on every quiz and exam. I will provide it. You don't need to print it out. And then finally, here's some advice from previous students about what they did to make an A. I told you already. Read the book. Come to class. Take notes. Study old exams. Those things, you'll make next class, I'm almost certain of it. Questions about the class?
Can we use our computers?
You can, but I think you'll find that you're better not having it. And I've already looked at it. Because you have this workbook, and I've created it for you to follow through. If you want to type it, you can, but I've already typed a lot of it. You can find this at the bookstore. I think it's like 15-ish, 16-ish dollars. And so,
that's our notes.
huh?
So that's our notes.
These are your notes. And so in class, like I have it too, and we'll just go through and we'll fill this out together. So you can absolutely use your computer out. I'm not offended by that, but I don't think you'll find it useful. Okay? What else?
For the textbooks, are we allowed to write or highlight on it?
Please don't.
Okay.
All right. You can use post-it notes and write those, but I expect to teach this class for many years. I don't want other students to use it. Yeah.
Mine is already highlighted.
I know. Okay. I know some of them are highlighted. Yeah, I bought them used on Amazon. I always watch Amazon, and when the prices dip down, I'll buy them. And the previous students have sold them to me. So, yeah, just treat them well. I know there's some amount of wear. Anyone else got one? No? Joseph, right? Joseph? Yeah. I want it back at the end of this. I won't post your grades. Okay. What else? Oh. So I like to have your pictures. Don't give me that. It's gonna be okay. So it's gonna work. You'll come up. This is alphabetical, and you'll understand underneath your name. Be sort of like mugshots. Sometimes I might ask you to step forward and say, "I didn't shoot the guy," or something like that. But you'll just stand underneath your name, and then I'll go on the next slide and then the next person. I don't post these pictures anywhere. I print them out, I put them in the front, but I never post them on Facebook or anything. So you'll never see this in the wider world. Okay? If you have an offense or whatever, take me taking your picture, that's fine, just sit it out. But let's go. You're pulling up. These 4 people. Don't hurt yourself. Think up yourself. And Haley, you're Haley, right? You're Haley. Do you mind doing, after I take your picture, can you do the clicker? Like, go to the next slide.
Oh, no.
Yep, no, good.
Oh, all four of us?
Yeah.
This is really good.
Michaela, is that right? And Gabrielle's not here, right? Huh?
We don't stand like this.
Okay.
I just want to see it.
It's a great fish. Haley, do you mind sitting up there?
Yeah.
7? What? All right, 1, 2. Okay, let's go over here. There's better light. All right, let's Zaria? Is that right? Zaria? No, over here. Zaria? Is that right? Marcia. Not Marsha. Okay, 1, 2, 3. Okay. You go on. Haley?
I changed it.
Hannah? Dawson's? Sean? Try to switch it up on me, I know. I'm sorry, Sean. All right, you ready? 1, 2, 3. 1, 2, 3. All right. Yara, Hackett, Brittany, and Anna.
I mean,
You don't have to smile.
you do a really egregious frown. Just make it interesting.
You can do like this. If you want. All right. 1, 2, 3. Mimi, how do you say your summer? It's summer, okay. Chastity and Sydney. Okay. All right. 1, 2, 3. Awesome.
So weird.
Sarah, April, Haley, Cam? You're April. Okay. Sarah? You're not here? Okay. All right. 1, 2, 3. Awesome. Madison or Maddie, Zach, Allie, Taylor. Huh? Zach, you like this. All right. All right. 1, 2, 3. Aaron, Emily, Leah? Is that right, Leah? Emily? Yeah. All right, 1, 2, 3. And one more. Haley, Tommy, and Kayla. Get everybody? Oh no, there was one more. Who's that other person? Janasia? Jack? Jack? Oh. Haley, Terry, not here? Are you always not wanting to take pictures? No, stand off to this side. All right, 1, 2, 3. Awesome. Thank you, Haley. All right, I want to do one other thing. Just want you to try using your clicker, please. Look, the code for your clicker is A. If you have an iClicker 2, when you turn it on, the prefix will come up AA or TT or AT. speed or whatever, and you need to change your frequency, you hold the power button down, and then you can set the frequency. AA is the default, so if you've never changed it, it should go to that. So AA is your frequency. And just put in the answer A, okay? Yeah. That's okay. All right, so we should have 35 people then. Does everybody have your clicker? Anyone else not have it? Two others? You have yours? Okay, how many doesn't have your clicker? Okay, 7, 8. Everybody clicked in? Yep, it's showing your response. Did you have your response? Okay, we'll use our clickers in the next several days. We'll take a few days to sort of iron out that kink. Have you used clickers before? Okay. Did you click in? Okay. Register on Moodle, please. I'm going to stop this. All right. So this first chapter is on standards. Standards and dimensional analysis. It's probably the most math that you'll see the entire semester. As far as, we don't do a lot of numbers, but we do some algebra and stuff. So don't freak out. The math sort of goes downhill from here. So whenever you measure a physical quantity, you're always comparing an unknown measurement to a known measurement. You think about it, anytime you make a measurement, that's what you're doing, is you're comparing an unknown thing to a known thing. Even if you step like on a bathroom scale, you're comparing your unknown weight to, if it's a spring scale, you're compressing some spring, and then that's calibrated to tell you what force is required to compress that spring. Or if it's one of those balance scales, it's doing some force calculations along the way. You're comparing an unknown quantity to a known quantity. So anytime you're making a measurement, you're comparing two quantities, one that's unknown and one that's known. And these known measurements are called standards. And there are three properties that are required for a good standard. They need to be accurate. They need to be unchanging. And third, sorry the three got cut off, it needs to be accessible. We'll talk about the different measurements, the different standards for the physical quantities that we'll measure in this class. And we'll talk about how they're either in the past, they haven't been accurate, they haven't been accessible, or they haven't been unchanging. So they don't meet the three attributes for a good standard. Today, really just recently, like last year, all of our standards for measurement have really come in line to meet these three attributes. But it's really just been in the last year that they've done so. We're going to have the SI system in this class. SI is French. It's for Système International, or the International System. There's an E at the end, and I think there's something else. But anyway, it's for the International System of Measurement. In particular, we're going to use the MKS subsystem of the SI system. We're only going to look at measurements for length, mass, and time. There are other standards for measurement that you would use, but we're just going to look at length, mass, and time. For most of our semester, that'll be sufficient. Later, in the latter part of this course, we'll get into electricity, and we'll have to introduce a new measurement for charge. And then later, when we get into light, we'll introduce a measurement for intensity. So that's how we measure the intensity of light. But right now, length, mass, and time. What do you think M, K, and S stand for? If we're talking about length, mass, and time, what does M, K, and S stand for? No, not mass. Meters, right? So they're the units for each of those. Meters, kilograms, and seconds. Those are the units that we'll use for length, mass, and time. In contrast, let me write that down. So you have meters, kilograms, and seconds. Some of you in the future will use the CGS system. Actually, a lot of people in health applications use the CGS system. What is CGS? Astronomers too use the CGS system, and sometimes chemists use the CGS. What does CGS stand for? Not meters, but centimeters, grams, seconds, still the same. Yeah, maybe use the CGS system? Use CCs, right? You know what CC stands for? Cubic centimeter, right? Use grams, you use kilograms too, I guess, but use grams for measuring different masses. And then, of course, we all use seconds for time. So, length, mass, and time, each of these need to be accurate, unchanging, and accessible. For the meter, the current unit of measurement for length is the meter. And the standard has changed over time. And it's kind of interesting to think about how the standard has changed, because it's changed in response to having these three attributes met. That is it accurate, is it unchanging, and is it accessible? The first thing is it was, in 1799, it was 1/10,000,000th. So a very small fraction of the distance from the equator to the North Pole. It was 1/10,000,000th the distance from the equator to the North Pole. So there are ways to measure that distance, and they said, okay, we're going to say 1/10,000,000th of that is the meter. Is that an accurate way to measure a meter? Yeah, no? Accurate? No, not a very accurate way to measure the meter at all, because it's very difficult to measure that distance, the distance from the equator to the North Pole, very accurately. One, where is the North Pole? Where is the equator? If you're just driving along out in wherever, you're not really clear where those points are. So it's not accurate at all. So it misses this, the first attribute. Is it unchanging, that distance? Sort of, maybe, but not really either, because, you know, it depends sort of how the landscape changes, how the oceans rise or fall. Is it accessible? You might be able to say that, yeah, everybody has access to the Earth, and so everybody has access to measure that. Whether it's accurate and unchanging or not, it still is accessible. So I'll venture that that standard does meet the third criterion. Until 1960, it was a bar in France. And not like a bar like a guy walks into a bar, but a bar like there was an actual bar that was 1 meter long. An actual bar, and that was the standard for measurement for all the world. So if you wanted to know what a meter was, you had to have that bar in some way, maybe a replication of that bar, a reproduction of that bar, but you had to have that bar, and then that defined what your standard for the meter was. Accurate? Is that accurate? If you have the bar, but what if you're trying to measure, I don't know, the width of an atom? Are you going to use a bar this long to measure the width of an atom? No. So I would argue that it might be accurate for some measurements if you have the bar. Or if you want to measure my height, that's plenty accurate enough for that. I'm about about 2 meters tall, a little less. But if you want to measure really small distances, then it's not really very accurate for that. So I'm going to give it a X on this one. Is it unchanging? You might think that it is unchanging, but in fact, it's not. We'll talk about this in relation to the standard for our mass. Not unchanging. Accessible to everybody? No, it's in France. Like, you have to, it was under lock and key. You couldn't get in to see the bar. They made reproductions of the bar, which they made meter sticks out of, right? And those were sent all around the world, but you can't get access to the true standard for the meter. And so it misses out on all 3 of those. Now, the standard of measurement is the distance that light travels in a certain amount of time. I'm going to give you the number. You don't need to know the number. I'm not going to mess you up by giving you a different number, but it's 1 over 3 times 10 to the 8th seconds. By the way, do y'all scientific notation? Do we do that here? I think we do it. No, we don't. Let me just give you a quick little primer. Y'all seen scientific notation before, I think? Well, let me just show you. Let's say I have 3.24. Don't write this down if it's easy for you. Times 10 to the 2. That means that is equivalent to 324. It's just 324 times 100 is equal to 324. I can also write small numbers. Like, let's say that I wrote 3.24 times 10 to the minus 2. That's equal to, write it down, what do you think? Don't say out loud, but just think for a second. On the first one, I moved the decimal place 2 places to the right. And so what's my answer here? Right, it's 0.0324. Look, I moved the decimal place 2 places to the right. I got that from here. Because this is -2, I'm going to move the decimal place 2 places in that direction. So it's 0.0324. So you'll see scientific notation some in this class, but that's how we just use it to write numbers in a particular way. It's not just to express big and small numbers. I'll show you what it means a little bit later. It has to do with our significant figures and how we express significant figures. Anyway, the distance the light travels. This meets all 3 of the criteria, 1, 2, and 3. It's accurate. We know the speed of light very, very accurately. We can measure it with great, great accuracy. So we know the distance that it travels in a certain amount of time, or the distance that it should travel, very, very accurately. Accurate enough to even use that standard to measure the width of an atom, for example. It's also, what's the second one? Unchanging. As far as we know, the speed of light doesn't change. We have no reason to think that it does, and it's never shown any change. So as long as we've been measuring it. And then finally, it's accessible. Anybody can measure the speed of light. It's really easy to measure the speed of light. It's an undergraduate experiment. Not in this class, but it's an undergraduate experiment to measure the speed of light. All you really need is like a little electric motor, a little laser, and a spinning mirror. And you're good to go. You can measure the speed of light with great, great accuracy. So it's a nice standard. No country holds it. It's very accessible. It doesn't change with time. And it is very, very accurate. All right. The mass is one of the more interesting because it recently changed. The current unit of measurement in the MKS system is the kilogram. In the past, the standard, these notes are old, they just changed this. I'm going to say the standard was a cylinder in France. It was like last November, I think, that they actually changed the standard. And this standard was not accurate. It was not unchanging. And it was not accessible. I'll show you a video about this and how the standard for the kilogram has evolved. But it used to be kind of like how the meter used to be a bar. There was a little cylinder in France that was a kilogram. By the way, a kilogram is a little more than a couple of pounds. Okay? So a typical person is about 70 to 80 kilograms. That's like 2 1/4 or 2 1/2 pounds. Okay? A couple of pounds. I got that? So there was a cylinder that was a little more than a couple pounds, and it was in France. They had it under lock and key. If you wanted to know what a kilogram was, you had to go to France. You had to get special pass to get into this place, and then you move on. There was the kilogram, and it was the definition for a kilogram for all the world. So it was not accurate, much like the bar. The meter wasn't accurate for measuring really small distances. The kilogram, this cylinder in France, was not accurate to measure very small masses, like the mass of an atom, for example. It was not accessible, and it turned out that the kilogram was losing mass. So it was not unchanging. So this standard for the kilogram is not ideal because it's not accessible, not accurate, and not unchanging. It changed with time. For several years, there were a couple of different contenders to be the new standard for the kilogram, and people poured billions of dollars into creating a new standard for the kilogram. But billions of dollars into creating a new standard. One of the standards was a sphere that was made out of silicon atoms. And you might say, a sphere of silicon, how is that different between a cylinder in France, right? But it was different because they were creating the sphere that had the same mass as the cylinder, and then they were counting the number of atoms inside of that sphere. And then the standard for the kilogram wouldn't be the sphere, it would be the number of silicon atoms in a kilogram. That would be based on the mass of a silicon atom. They use silicon because silicon is really rigid, it's really regular, and so you can count the number of atoms readily. The other was a balance, where it's a little bit complicated. It was sort of a balance, like you think of Lady Justice holding the balance, right? That it was a balance that converted the mass of the current kilogram standard, that cylinder in France, to an electrical signal. And it based the mass of that kilogram on this electrical signal, on a constant called Planck's constant. The winner, the silicon atom, or Planck's constant? Which do you think? You're right. Yes, Planck's constant. So the current standard for the kilogram the kilogram is based on Planck's constant. It's P-L-A-N-C-K. It's named after a famous physicist from the early 1900s with a watt balance. Okay, let me show you a video. I'll bring this back in just a second. Let me show you a video. Oh, where is it? Oh, here we go. So again, billions of dollars they put into creating this new standard of mass. And that's why I just want to drive home the importance of these standards. That they are incredibly important for everybody, no matter what kind of field you're in. Because it's how we function. Like it's how the markets function, measuring things. It's how healthcare functions, that you measure all sorts of things. And you have to know these standards of measurement. Okay? So we did what? Length is based on the speed of light. I want you to know too that I might ask you about some of the past standards for these length, mass, and time where I get them to you. So make sure you know those. You'll see some of the questions on the old test. All right, one more. Is time. So the current unit of measurement is the second. And the standard used to be based on the the fraction of a solar day. And now the second is defined by the period of an oscillating cesium atom. So there are certain atoms that oscillate at a very regular rate, and cesium is one of those. It goes back and forth, back and forth, back and forth at a very particular frequency, and so we can use that to measure a second. We say that a second is so many millions of oscillations of the cesium atom. This is accurate, this is accessible, and this is unchanging as far as we know. Oh, let's see. Let's try a clicker question. All right. I like these questions where I give you multiple options and you have to pick the ones that are correct or incorrect, so get used to them. They're good questions for exams. Which of these is a reason or reasons that a standard of measurement is not appropriate? You can ask your neighbor what they put. In fact, I encourage you to do so. That if you're not sure what the answer is, or if you are really sure, just talk to your neighbors in your immediate vicinity, ask what they put. Ask them why they put what they put. In fact, let's let everybody ask somebody that's close to them what they put. See if y'all have the same answer. Marcella, you share your answer with Kiara and Madeline next to you. Has everybody shared your answer with somebody else? So which of these is a reason that would make a standard of measurement not a good standard of measurement? Okay. Or have it wrong and right now. Ask your neighbor what you put. If the standard changes, does that mean that it's not appropriate? If the standard is not available, does that mean that it's not appropriate? If the standard is based on some obscure physical constant, does that mean it's not appropriate? If it smells really bad? All right, we're about evenly split. In fact, about half the class put A, and about half the class put E. So we're evenly split between A and E. Now ask around. Ask what y'all put. Why did you put what you put? It is either A or E. There's one person that has D, but not D. All right, I'm going to stop here at 250. 250.
Yeah.
Okay, E is the right answer, because if a standard changes and if it's inaccessible, that means that it's not appropriate. Okay? If these two are true, that means that it's not an appropriate standard. It doesn't matter if it smells really bad. Who cares if it smells bad, right? That it can still be a good standard. And if it's based on some obscure physical constant, right? Planck's constant, most of you probably never even heard of Planck's constant, right? But it's now the standard for mass. The speed of light, you probably knew the speed of light. But what was the frequency of the cesium atom? You probably didn't know the frequency of the cesium atom before, or that it even had a frequency. And it does, and that's our standard for time. That's how we measure the seconds that pass in this class. They go slowly. Let me tell you something about class. I never let you out early. I try not to let you out early, okay? Because you pay good money to be here. And so let's get used to it. You'll get to hang out. I know that Tuesday, Thursday classes are kind of long, but I like to do it all the time. Never let you out early. I never start late. I try not to do either of those because your time is very valuable. So know that if you come here, that we're going to be here the whole time. Okay? Is that cool? So, all right, so we have about 13 more minutes, 11 more minutes. All right. All right. Let's do dimensional analysis. I'm going to give you, let me go ahead and give you actually your metric prefixes. We don't really use them that much, but let me give them to you anyway. You'll see them periodically. Micro, milli, centi, kilo, mega, and giga. I know that you learned these at some point in high school, physical science or math, but if you didn't, that's okay. Micro is 10 to the minus 6, milli is 10 to the minus 3, centi is 10 to the minus 2, kilo, so sort of passing over from small to big, kilo is 10 to the 3rd, mega is 10 to the 6th, and giga is 10 to the 9th. Centi is sort of the one that stands out because we have, 6, 3, 3, 6, 9, so we have this minus 2. What this means is the 10 to the minus 2, for example, is that in a meter? This is a meter. The 10 to the minus 2 means that a meter is a centimeter is 1/100th of a meter. A centimeter, which has the centi prefix, is 1/100th. That's what 10 to the minus 2 means. It means 1 over 10 to the 2, or 1 over 100. So a centimeter is 1/100th of a meter. Or you can think of it, like I like to, that there are 100 centimeters in a meter. Okay? Or how many grams are in a kilogram? That's the question. How many grams are in a kilogram? 1,000, or 10 to the 3rd. 10 to the 3rd is a 1 with 3 zeros after it, or it's 10 times 10 times 10, or 10 to the 3rd. So there are 1,000 grams in 1 kilogram. There are 1,000,000 meters in a megameter, for example, and on and on. You're not going to have to convert between these units, but you'll just see these units along the way. I just want you to have a feel for their values. Okay, we'll come back. I'll remind you of these along the way. All right, let's do some dimensional analysis. These are going to be useful for you because as we move forward, we're going to do some, as I said, relational problems. Not like, man-woman relational problems, but how do variables relate to other variables? So if I have an equation and I have one variable and how it changes, I want to know how other variables will change. You'll see what I mean as we move along. But being able to do dimensional analysis will help you to be able to do that. First, let me give you some common dimensions and units. Area is a length times a width. And so this is often, usually, in units of square meters. If you're in the MKS system, it's always in square meters. Volume is length times width times height. And so it's in units of cubic meters. Velocity is a distance divided by time. So it's in units of meters per second. And acceleration is a velocity over time. And velocity over time is going to be meters per second, which would be meters per second squared. We'll get more into those in the first chapter, the velocity and the acceleration especially. But just for now, just want you to know the units for these: area, volume, velocity, and acceleration, to help us do these dimensional analysis problems. So I'm going to give you some equations, and I want you to tell me if they're dimensionally correct or not. And the way I'll help you with this first one, and I'll give you 3. I want to know, are these equations dimensionally correct or not? And the way that I do that is I ask the question, do the dimensions on this side match the dimensions on the opposite side. So I know that this is x. It's a measurement for distance, which is going to be in meters. This is velocity, meters per second. This is time, seconds. Does the dimensions on this side of the equation match the dimensions on this side of the equation? Don't answer that. Let's write it out first. So x is in meters. I'm just going to rewrite the equation just with the dimensions. And I'm asking the question, is it equal to the dimensions of the other side? V is meters per second. And then t, I'm going to write t like this. I'm going to write it as like t over, well, I'm sorry, not t, but seconds. When I have a fraction like I have here, I like to write everything as a fraction, even if you otherwise wouldn't write it as a fraction. But seconds is the same as seconds over 1. Are those two mathematically equivalent? The seconds cancel, right? So those are equivalent because these two cancel out, and so this is dimensionally correct. On this next one, I'll let you do this one. I'm going to give you a little help first. You're going to do exactly the same thing. And what you have to show, if it's dimensionally correct, you have to show that the dimensions for each part are all the same. So I know this is in meters, for example. And so the rest, all the other parts have to also be in meters. This x with a little 0 subscript, that has to be in meters. This v, the t, or this v times t, that has to be in meters. And then this 1/2 at squared also has to be in meters. Let me say a couple of things. The half, the 1/2 is a constant. And so when I'm considering the dimensional relationships, it doesn't count. So I can get rid of the half, just forget about it. So I'm just going to say this right here is a constant, and so it doesn't matter when I'm looking at how variables relate to one another. The other thing is I've used a new symbol here, this 0. What this means, if I were to write it out longhand, it would mean x at t equals 0 seconds. So that is the initial position. It's the initial position. We often say this as x naught, like naughty, but not like 0. So x naught is the way that you would say that. The 0 just means your initial value for whatever that is. You'll see that come out throughout the semester. Don't be blown away by it. Sometimes it's written not as x naught, but it's written as x with an I subscript. What does the I mean? Initial. Okay, but in physics we usually use the 0 just because we like to create this secret language that other people don't know so that it confuses other people so that they don't try to come in and take our jobs. Okay? Oh, did I just say that out loud? Okay? So tell me, is this dimensionally correct or not? Or not? Not. And remember, this is a not. The dimensions of this are the same as this. The not doesn't really matter. It just means the initial value. All right, let's do this as a clicker. A will be yes, it is dimensionally correct. Or B will be no, it is not dimensionally correct. Right, we've already done this. You know the dimensions of that little thing. So you really just have to look at that last one. Please note that T is squared and A is in units of meters per second squared. A is the acceleration. A yes, B no. And we have equal values. Half of you think yes, half of you think no. Ask your neighbor, share your notes, what you did, how you did it. All right, we'll stop here in just a few seconds. I'm going to stop at 1:30, so get your final answer in. Just guess if you don't know, and that's perfectly fine. All right, so let's see. A is the right answer. It is dimensionally correct. And I can look at each term. On the left, X is in meters, X naught, we also know is also in meters. Remember, I'm just looking that every term is the same. I already know that V naught T, which is the same as this, but that's meters, because it's meters per second times seconds, so the seconds cancel. And so really it's just this last part. I just leave off the half. It doesn't have any units at all. A is meters per second squared. T squared is seconds, but it's squared. I'm going to put that over 1. And so these units cancel out. I'm left with meters all the way throughout. And so A is the right answer. We'll do some more of those next time on Thursday. And I'll see y'all then, okay? We're looking for a reading quiz next week. It's probably going to be on Thursday. I'm going to be out of town. I'm going to have my secretary come in and talk about it. But that'll be all that you do on that day. More about that next week. But be reading chapter 1, okay? It will cover chapter 1.